the floor where they drop like bombs. Faceless voices running all the cons. Digital whispers in the binary night. No light, no face, pure sound, no sight. Stories unfold in the dark unscrolled. Echoes of silence, secrets untold. Waves crash loud in this audio cave. No mic, no fame, just the sound we crave. Tune and turn up, let the silence break. Raw, unfiltered, hear the earthquake. No mic needed, just a vibe that's real. Faceless words you can touch and feel. In shadows, voices untamed. No need for spotlight, no claim to fame. Just a beat of life in a stream of thought. Every word a punchline, no need to be taught. Just listen close, no visuals needed. Raw conversation, unprocessed, unseated. Feel the pulse in every sentence said. No distractions, just thoughts in your head. Whispers of the streets, rumbling through. Faceless yet vivid, a world in view. No mic, just souls, connecting in flow. Pure and raw, let the rhythm go.
The pursuit of science has often been compared to the scaling of mountains, high and not so high. But who amongst us can hope, even in imagination, to scale the Everest and reach its summit when the sky is blue and the air is still, and in the stillness of the air survey the entire Himalayan range in the dazzling white of the snow stretching to infinity? None of us can hope for a comparable vision of nature and of the universe around us. But there is nothing mean or lowly in standing in the valley below and awaiting the sun to rise over Kanchenjunga. Subrahmanyan Chandrasekhar, Truth and Beauty, Aesthetics and Motivations in Science. Subrahmanyan Chandrasekhar, Nobel laureate astrophysicist, renowned for his work on stellar structure and evolution, particularly the Chandrasekhar limit, defining the maximum mass of a stable white dwarf star. Subrahmanyan Chandrasekhar, born in Lahore, British India now Pakistan in 1910, displayed exceptional intellectual precocity from a young age. His family, though not wealthy, fostered a strong academic environment. His father was a government auditor, and his uncle was the Nobel laureate physicist C.V. Raman. Chandrasekhar's early education took place in Madras, now Chennai, where he excelled in mathematics and physics. He was particularly drawn to the intricacies of numbers and the fundamental laws governing the universe. This fascination led him to devour textbooks and scientific papers far beyond his prescribed curriculum. By his teenage years, he had already demonstrated a deep understanding of advanced mathematics and physics, laying the groundwork for his future groundbreaking contributions to astrophysics. His early studies were marked by a fervent desire to comprehend the cosmos, a driving force that propelled him through his formative years and towards a path of scientific discovery. Subrahmanyan Chandrasekhar's initial foray into scientific publication occurred in 1929, while he was still a student at Presidency College in Madras. This first paper, titled The Compton Scattering and the New Statistics, delved into the intricacies of the Compton effect, a phenomenon where photons scatter off charged particles, typically electrons, resulting in a change in wavelength. This work was significant as it also incorporated the new statistics, referring to the then emerging field of quantum statistics, which provided a more accurate description of the behavior of particles at the atomic and subatomic levels. Chandrasekhar's exploration of the Compton effect, intertwined with the principles of quantum statistics, demonstrated his early grasp of complex theoretical physics. Even as a young student, he was engaging with cutting-edge scientific concepts and striving to provide a more refined understanding of fundamental physical processes. It is also noted that he had a paper published in the Indian Journal of Physics in 1928, titled Thermodynamics of Compton Effect with reference to the interior of the stars. Therefore, he had multiple papers published while he was still a student. Subrahmanyan Chandrasekhar successfully completed his doctoral studies at Cambridge, receiving his PhD in the summer of 1933. His dissertation focused on the complex behavior of rotating, self-gravitating polytropes. Demonstrating exceptional academic achievement, he was subsequently elected to a prestigious prize fellowship at Trinity College, a significant recognition that placed him among an elite group of scholars. This election held particular historical significance as he became only the second Indian to receive such an honor at Trinity, following the legendary Srinivasa Ramanujan. Interestingly, Chandrasekhar had anticipated failure in his fellowship bid, having already made arrangements to continue his studies under E. A. Milne at Oxford, even securing accommodation there. During his time at Cambridge, he formed an acquaintance with the prominent British astrophysicist Sir Arthur Eddington. While Eddington initially showed interest in Chandrasekhar's work, their relationship took a contentious turn when, in 1935, Eddington publicly and vehemently criticized Chandrasekhar's findings, leading to a significant scientific dispute. In 1935, an invitation from Harlow Shapley, the director of the Harvard Observatory, brought Subrahmanyan Chandrasekhar to the United States as a visiting lecturer in theoretical astrophysics. During his 3-month stay, he made a strong impression on Shapley, though he declined a research fellowship offered by Harvard. Around the same time, he connected with Gerard Kuiper, an expert on white dwarfs who was then associated with the Yerkes Observatory at the University of Chicago. Otto Struve, Yerkes director, was considering Chandrasekhar for a faculty position, prompted by Kuiper's recommendation. While initially hesitant, Chandrasekhar eventually accepted the offer and joined Yerkes as an assistant professor in 1936, following a persuasive radiogram from the university's president, Robert Maynard Hutchins. Notably, Hutchins also intervened to ensure Chandrasekhar was allowed to teach, overriding racial prejudice from a dean. Chandrasekhar remained at the University of Chicago for his entire career, progressing through the ranks to become a full professor by the age of 33. The University of Chicago demonstrated their commitment to retaining him, even matching a significantly higher salary offer from Princeton. 1939 to 1943, he delved into stellar dynamics, examining the motions of stars within galaxies and the forces governing their distribution. Simultaneously, he explored the theory of Brownian motion, analyzing the random movement of particles. 1943 to 1950, his attention turned to radiative transfer, studying how energy moves through stellar atmospheres, and the quantum theory of the negative hydrogen ion, a crucial factor in stellar opacity. During World War II, Subrahmanyan Chandrasekhar contributed his expertise to the war effort by working at the Ballistic Research Laboratory in Aberdeen Proving Ground, Maryland. His work there focused on ballistics, resulting in a series of technical reports that addressed problems related to shock waves, projectile velocity, and blast wave reflection. His deep understanding of hydrodynamics, a field he had extensively studied, drew the attention of Robert Oppenheimer, who invited him to join the Manhattan Project at Los Alamos. However, due to delays in obtaining the necessary security clearance, Chandrasekhar was unable to participate in the project. There have been unsubstantiated reports that he visited the Calotron Project, which was also part of the Manhattan Project. He became a distinguished service professor in 1952, and, along with his wife, became a U.S. citizen in 1953. Later, he occupied an office at the Laboratory for Astrophysics and Space Research, and resided in apartment buildings near the university. 1939 to 1943, he delved into stellar dynamics, examining the motions of stars within galaxies and the forces governing their distribution. Simultaneously, he explored the theory of Brownian motion, analyzing the random movement of particles. Principles of Stellar Dynamics 1942, this book solidified his contributions to the understanding of the motions of stars within galaxies and star clusters. It became a standard text in the field. 1943 to 1950, his attention turned to radiative transfer, studying how energy moves through stellar atmospheres, and the quantum theory of the negative hydrogen ion, a crucial factor in stellar opacity. Radiative transfer 1950, this comprehensive work explored the theory of how radiation propagates through stellar atmospheres and other astrophysical environments. It is considered a foundational text. 1960s, he explored the equilibrium and stability of ellipsoidal figures, and began his studies of general relativity. 1950 to 1961, he concentrated on turbulence and the complex areas of hydrodynamic and hydromagnetic stability, investigating fluid behavior and magnetic fields. Hydrodynamic and Hydromagnetic Stability 1961, this book detailed his extensive research into the stability of fluids, including the effects of magnetic fields, a critical area in astrophysics and plasma physics. Ellipsoidal Figures of Equilibrium 1969, this work explored the equilibrium and stability of rotating fluid bodies, contributing to the understanding of celestial bodies' shapes and dynamics. 1971 to 1983, he dedicated himself to the mathematical theory of black holes, producing significant work in this complex field. The Mathematical Theory of Black Holes 1983, this book is a very in-depth mathematical explanation of the theory of black holes. Late 1980s, finally, he worked on the theory of colliding gravitational waves, further expanding his contributions to general relativity. Newton's Principia for the Common Reader 1995, towards the end of his life he worked on making Newton's Principia accessible to a wider audience. Subrahmanyan Chandrasekhar died on August 21, 1995, in Chicago, Illinois, at the age of 84. His death followed a heart attack. He had remained intellectually active throughout his life, continuing his research and writing. His passing marked the end of a remarkable career that significantly advanced the field of astrophysics. Actually, under stellar conditions matter is generally so highly ionized that, as we shall see in greater detail in Chapter 7, the uncertainty in the chemical composition is essentially due to the uncertainty in the abundance of the two lightest elements, namely, hydrogen and helium. The abundance of the lightest elements has then to be considered as a fresh parameter in the discussion. We can thus summarize by saying that our fundamental problem is to seek a theoretical relation of the kind Fl, m, r, abundance of hydrogen and helium equals 0. Subrahmanyan Chandrasekhar, An Introduction to the Study of Stellar Structure. Subrahmanyan Chandrasekhar received numerous prestigious awards throughout his distinguished career. Here are some of the most notable: Nobel Prize in Physics 1983, for his theoretical studies of the physical processes of importance to the structure and evolution of the stars. Copley Medal 1984, Royal Society's highest award. National Medal of Science 1966, United States' highest scientific honor. Royal Medal 1962, awarded by the Royal Society. Padma Vibhushan 1968, India's second highest civilian award. Bruce Medal 1952, awarded by the Astronomical Society of the Pacific. Gold Medal of the Royal Astronomical Society 1953, Henry Draper Medal of the National Academy of Sciences 1971, Danny Heinemann Prize for Mathematical Physics 1974, Adams Prize 1948, Rumford Prize 1957, reference and citation, Chandrasekhar, S. 1931. The maximum mass of ideal white dwarfs. The Astrophysical Journal, 74, 81-82. Chandrasekhar, S. 1939. The Dynamics of Stellar Systems. I. 8. The Astrophysical Journal, 91, 1-154. Chandrasekhar, S. 1942. Principles of Stellar Dynamics. University of Chicago Press. A fundamental textbook. Chandrasekhar, S. 1943. Stochastic Problems in Physics and Astronomy. Reviews of Modern Physics, 15-1, 1-89. Chandrasekhar, S. 1943. On the Decay of Plane Shock Waves. Ballistic Research Laboratory Report Number 345. Chandrasekhar, S. 1950. Radiative Transfer. Clarendon Press. Chandrasekhar, S. 1957. An Introduction to the Study of Stellar Structure. Dover Publications. Chandrasekhar, S. 1961. Hydrodynamic and Hydromagnetic Stability. Clarendon Press. Chandrasekhar, S. 1968. Some Historical Notes on the Neutrino Problem. Proceedings of the National Academy of Sciences of the United States of America, 59-4, 1111-1119. Showing his historical perspective on physics. Chandrasekhar, S. 1969. Ellipsoidal Figures of Equilibrium. Yale University Press. Chandrasekhar, S. 1983. The Mathematical Theory of Black Holes. Clarendon Press. Chandrasekhar, S. 1987. Truth and Beauty, Aesthetics and Motivations in Science. University of Chicago Press. His Philosophical Perspective on Science. Chandrasekhar, S. 1995. Newton's Principia for the Common Reader. Clarendon Press. Volley, K.C. 1991. Chandra, A Biography of S. Chandrasekhar. University of Chicago Press. Parker, E.N. 1997. Subrahmanyan Chandrasekhar. Biographical Memoirs, 72, 29-48. Taylor, R.J. 1996. Subrahmanyan Chandrasekhar. Biographical Memoirs of Fellows of the Royal Society, 42, 79-94. Saikya, D.J. and Trimble, V. eds. 2011. Fluid Flows to Black Holes, a tribute to S. Chandrasekhar on his birth centenary. World Scientific. I was very fortunate to know the great astrophysicist Subrahmanyan Chandrasekhar during his last years. Chandra, as we called him, was the first to discover that general relativity implied that stars above a certain mass would collapse into what we now call a black hole. Much later, he wrote a beautiful book describing the different solutions of the equations of general relativity that describe black holes. As I got to know him, Chandra shocked me by speaking of a deep anger toward Einstein. Chandra was upset that Einstein, after inventing general relativity, had abandoned this masterpiece, leaving it to others to struggle through it. Lee Smolin, Einstein's Legacy. Where Are the Einsteinians? 2005.
Mics on the floor where they drop like bombs. Faceless voices running all the cons. Digital whispers in a binary night. No light, no face, pure sound, no sight. Stories unfold in the dark, unscrolled. Echoes of silence, secrets untold. Waves crash loud in this audio cave. No light, no fame, just the sound we crave. Tune in, turn up, let the silence break. Raw, unfiltered, hear the earthquake. No mic needed, just the vibe that's real. Faceless words you can touch and feel. Hidden in shadows, voices untamed. No need for spotlight, no claim to fame. Just the beat of life in a stream of thought. Every word a punchline, no need to be taught. Just listen close, no visuals needed. Raw conversation, unprocessed, unseated. Feel the pulse in every sentence said. No distractions, just thoughts in your head. Whispers of the streets, rumbling through. Faceless yet vivid, a world in view. No mic, just souls, connecting in flow. Pure and raw, let the rhythm go. Pure and raw. Pure and raw. Turn up, let the silence break. Raw, unfiltered, hear the earthquake. No mic needed, just the vibe that's real. Faceless words you can touch and feel. Tune in, turn up, let the silence break. Raw, unfiltered, hear the earthquake. No mic needed, just the vibe that's real. Faceless words you can touch and feel. Pure and raw.
Okay.